Picture this, 10,000 feet of steel pipe hanging straight down from a massive drill ship right through the open ocean, connected to a wellhead that's actively containing pressures that could reach 15,000 pounds per square inch. Welcome to this explainer on the marine riser. It's not just a pipe, it is the drill ship's massive, physical, and pressure-rated umbilical cord to a live well.
What's truly mind-boggling here is the sheer scale of what we're talking about. Imagine 10,000 feet of steel dangling from a ship, fighting off pressures that can hit 15,000 psi. Every single joint, every single connection has to survive violent vessel motion, deep-sea ocean currents, and extreme internal pressure, all at the exact same time. It's honestly wild.
So, here's our roadmap for today. We're going to cover the 10,000-foot umbilical, the anatomy of a riser, how it absorbs ocean motion, and high-pressure redundancy. Let's kick things off with Section 1, the 10,000-foot umbilical, connecting the ship to the seabed. So, what exactly is the marine riser? Well, it's essentially a continuous, highly protected string of large-diameter pipe joints. It physically connects the drill ship up on the surface directly to the subsea wellhead and the blowout preventer, or BOP stack, sitting way down in the dark on the seafloor. Without this crucial system, any drilling mud returning from the well would just dump straight into the open ocean, and the drill string would have literally no protected path to the seabed. Think of it as the ultimate structural highway between the ship and the earth. This sets up what I like to call an impossible engineering paradox. Think about it. How on earth do you connect a ship that never ever stops moving to a totally static seabed without the pipe just snapping in half? You've got the drill ship up top dealing with constant wave heave, wind, and powerful surface currents, and then thousands of feet below you have the seabed and the BOP, entirely rigid and locked in place under extreme deep water pressure.
The absolute key takeaway here is that the riser isn't just some long, dumb tube passively hanging in the water. No, it is a highly responsive, actively tensioned structural lifeline. It has to stay completely rigid relative to the seabed, even while the ship it's attached to is tossing around in massive ocean swells above.
Okay, moving on to Section 2, Anatomy of a Riser, the giant straw. I want you to picture the riser as one very large, super strong 21-inch outer diameter straw. But bundled tightly alongside it are these smaller, extreme pressure emergency straws running down its entire length. You've got the main bore, which houses the drill string and returns the mud. Then, strapped to the outside, you have your dual choke and dual kill lines. These bad boys are rated to a staggering 15,000 psi because they act as your emergency well control brakes. Plus, there's a booster line rated for 7,500 psi to help push mud circulation. All these auxiliary lines are bundled together with the main pipe into one massive, cohesive assembly.
Now, calculating the length of this giant string is incredibly precise work. The standard 21-inch seamed joints are stacked sequentially, one after another. But here's the catch. The ocean floor doesn't just conveniently sit at perfectly exact standard joint increments, right? So to make up the difference, the crew uses shorter pipe segments called pup joints to fine-tune the exact length needed to perfectly reach the seabed for that specific water depth. Every single foot is meticulously accounted for.
That brings us to Section 3, Absorbing Ocean Motion, the telescopic joint.
Let's zoom in on this telescopic joint. It sits right at the top of the riser string, just below the drill floor. Much like the accordion connector you see between two train cars, flexing while the actual cars stay rigid, the telescopic, or slip joint, slides up and down to absorb the ship's motion. As a massive ocean swell pushes the drill ship up, the sleeve extends. As the ship drops down into a trough, it compresses. It's honestly engineering magic, and it's exactly what prevents the 10,000 feet of rigid riser below from bending, twisting, or taking on unthinkable structural loads.
Let's wrap up with Section 4, High-Pressure Redundancy, the Rule of 2. We keep throwing around this number, 15,000 psi, for those emergency lines. Let's put that into perspective for a second. That is roughly 500 times normal atmospheric pressure. 500 times! At that level of extreme pressure, even minor wear on these joints is a critical well control threat. We're not talking about a cosmetic issue here. These lines are literal pressure vessels operating under immense loads.
And because the stakes are so high, we have the rule of 2. The choke and kill lines, they are absolutely always duplicated. During a blowout or emergency situation, sudden pressure and temperature drops can cause these ice-like blockages called gas hydrates to form.
If one of those emergency lines gets plugged up with hydrates, the duplicate line is right there as an immediate, fully independent backup pathway to save the rig. When you are physically connected to a live well, a single point of failure is simply never acceptable.
So when we pull all this together, you can really see how this system is pulling off 4 incredible, simultaneous feats of engineering all at once. It safely contains the heavy returning drilling mud. It provides a continuous, protected, physical path for the drill string to reach the earth. It serves as a 15,000 psi emergency barrier straight back up to the ship. And somehow, it absorbs constant, unrelenting vessel heave without failing. I want to leave you with a provocative thought here. Now that we know just how heavy and rigid this entire system is, how on earth do they hold it all up and keep it perfectly tensioned from the surface? Think about it. 10,000 feet of steel is incomprehensibly heavy. How do they keep it from just collapsing straight into the ocean under its own weight while the ship bounces on the waves? Well, that is a massive engineering puzzle involving some seriously heavy-duty tensioners, and it's exactly the question that should make you want to jump into our next explainer. Thanks for learning with me today.